Hello. I think we're live. Yeah, my streaming, well, not the streaming software, but the YouTube dashboard. My God, I already can't speak. YouTube dashboard was being a bit weird, but I think we're good. Um, yeah. Okay. Cool. Well, welcome everyone to a bit of a weird one, actually. I was sort of debating whether to do this or not. But I figured, especially after yesterday's video, if people didn't see that, it was basically just a video of me saying that I couldn't get a job. So one of the things that one of the things that I've needed to do is kind of knuckle down and get on with learning or like solidifying, because I did read a book technically, but you read a book and it goes in and then it goes out the other end. So I need to kind of solidify my knowledge of data structures and algorithms, and then at some point I'll probably start doing some leak code stuff as well. I might do kind of some like of this course and then move on to doing leak code stuff, which I've always been kind of against leak code, but not like some kind of moral thing. It's just I don't know if I really enjoy it that much. I've never really had much of a desire to do it, but it's one of those things where you kind of have to do it. Although, I mean, the issue that I've been having is that I can't really get an interview. So it's like even if I did leak code and sort of became really good at solving those kind of problems, I wouldn't really have a chance to even showcase that. But anyway, we'll do it anyway. I think we're good. I was getting a warning then from YouTube, but I think we're good. It was warning me about bitrate, but I think I'll have to look into it. I think it's fine for now, but we'll go with it. But yeah, I'm using boot.dev, which is a really cool site. I did a course on here, which was where is it? Memory management in C. So I actually finished this course. Really good course, very interesting. You sort of make your own kind of language to some extent, not like fully, but you kind of implement like a garbage collector and stuff, and it's quite cool. Really useful. I like learning about C. I kind of want to use C at some point. I just don't really have much of a use case at the moment. Although I do want to do the kind of project I had in mind was like an operating system. I thought that would be really cool to do something like that. And there is a thing on it. I do actually have something kind of saved. This thing here, which is oh, it's telling me that. Oh, okay, my bitrate is low, but my bitrate is quite. I don't know. I don't think it really matters. But anyway, yeah, there is this, which is like the little book about OS development, which seems pretty cool. I don't know how good it is, and I know that I think I read it was somewhere in here, basically just talking about the book, and it basically says like the first kind of few parts of this, it'll kind of go into detail about what you need to do, but then afterwards it kind of gets more and more like just the theory, and then you kind of have to implement it yourself. So it'll be a difficult one, and it'll be interesting. And I think there was something in here about like the people that made this book. It took them like 6 weeks to like build the thing. So probably going to be a long project, but it'd be really cool to get something going. So yeah, might have to look at that at some point. I've also got like I'm also part way through reading crafting interpreters as well, building a language in that, which is pretty cool. I need to finish that off. I do this thing where I start reading something and then I don't actually finish it, so I need to actually finish that book and but I think I'm going to do a video on it at some point just to kind of highlight it and be like, you should check this out. It's pretty cool. So yeah, that's pretty much it. But yeah, like I said, I'm going to be using boot.dev. I think it's fine to stream this because technically speaking, the courses are free. You can go on and like read the content. You get like a couple of these, so you get like it's split into chapters. So if you're on like a free account, you can usually do like the first couple of chapters completely free, like fully interactive. So you can do the quiz stuff and you can write code. But then after that, they become like read only. So and then you have to buy a membership if you want to do like the follow along with the programming and stuff. But you can just read them. So I think me doing this is completely fine, but I don't really know. So if it is an issue, I'm sure people from boot.dev can let me know, but it should be fine. Because technically speaking, you can go on here and just read all this stuff for free anyway. So yeah. But yeah, I'm going to get on with this. I don't know if I'm going to read stuff out, but I might read it out in bits anyway. Maybe discuss it if anybody's in here and wants to discuss stuff. But yeah. So some of this stuff I do know. Oh, actually, I need to change. Oh my god. Okay, I need to select my quest. So I'm going to do 3,000 XP because I reckon I'm going to do quite a few of these. So I should hopefully be able to hit that target. And I'd have to buy a potion. Let me just check. Oh, how many gems do I have? Oh, I have Frozen Flame. Yeah, I really like. Let's get rid of this because I don't really ask Boots questions, so I tend to sell the salmon. And then I can buy a potion, which gives you 25% XP. That's pretty cool. If I do this, there we go. So for the next hour, got an extra 25% XP. All right, let's do this. So constants don't matter. So this I do know. I'm sort of, where am I? On chapter 2, and I'm kind of, I'm like halfway through chapter 2. So I've sort of done some stuff, but you won't really have missed much if if you started from here. Well, you will have done, but like it doesn't really matter that much. And you can always go back and look at the earlier things. But it's just the thing about math, like understanding what factorial is and what exponents are and stuff like that. So that's obviously quite important. But anyway, on with this. So it only describes the theoretical growth rate of algorithms. It doesn't deal with the actual time an algorithm takes to run on a given machine. As such, when doing big O analysis, we don't let ourselves get bogged down in details. For example, take a look at the following functions. This is all in Python as well, by the way, which I'm not really... I haven't done a lot of Python, but I've kind of struggled my way through it. And it's actually, it's actually quite like a nice language to use, to be honest. Maybe I'll do more Python in the future. Anyway, yeah, as you would expect, print names 1 will take half the time to run as print names twice. And in the real world of software engineering, cutting speed in half is awesome. The funny thing about big O analysis is that we don't care. We're academics. That's not true in my case. Both of the functions above have the same rate of growth, ON. You might be tempted to say print names twice should be 2 times n, or 2n. But you would be missing the whole point of big O. In big O analysis, we drop all constants because while they affect the runtime, they don't affect the change in runtime. Okay, that makes sense. Yeah. Yeah, sorry if you can hear the neighbor's dog barking, by the way. I don't think the mic picks it up, but I can certainly hear it. Anyway, so we need to listen to this guy talking. So I'll put my headphones on and we'll listen to this. I did test it beforehand, so hopefully it's not too loud, but do let me know if it is.
Big O notation only cares about the theoretical slowdown of an algorithm as its input size grows. It doesn't actually care about how long, like in seconds, this algorithm is going to take to run. So when I say if a linear time algorithm takes 1 nanosecond to run with an input size of 1, then it will take about 10,000 nanoseconds to run for an input size of 10,000. Like, that is true, but whether or not it actually takes 1 nanosecond on an input size of 1 or 1 full second on an input size of 1 is actually completely irrelevant to Big O. All we care about is the proportional change from 1 item to 10,000 items. We don't care about how long it actually takes. And when I say we don't care, I mean we don't care as computer scientists doing this theoretical exercise. Of course, as software engineers, we care. No one cares if the Big O of your website's load time is constant. If it actually takes 5 seconds to load, that's a terrible experience. So as software engineers, we do care about constants, but when we're doing Big O analysis, we don't really care. We just kind of brush it aside. We hand wave it away. Say you have a function running in production, and it takes 5 seconds to run on an input size of 10,000. Then you benchmark it again on an input size of 10 million, and it still just takes 5 seconds to run. Well, That's actually a constant
I vied
time
so
algorithm.
hard and-
The runtime isn't being affected by how big the input size is. But whether or not 5 seconds is actually tolerable by your users is up to your users, I suppose. But why this matters is that 5 seconds in big O terms, we just don't care. We don't say, oh, it's order 5 because it took 5 seconds. We just say it's order 1 because it's constant. So that constant can always just be reduced to 1. Let's take a look at another concrete example. Here we've got a function called sum. Takes a list of numbers, iterates over all the numbers, summing the result as it goes, and returns it. This is fairly obviously an order n algorithm. Now this is interesting. Let's say we take another function. This one's called triple sum. It iterates over every item in the input once, summing the items as it go. But this time, it does it again and again. So just looking at this function, you can tell this function takes 3 times as long to run as the first one. Instead of looping over the input once, we're doing it 3 times. So if the first algorithm is order n, wouldn't this one be like order 3n? And the answer is yes, but we don't care. We're doing big O analysis. Constants don't matter. So that 3 just reduces to a 1, and we get order n again.
All right, that makes sense. So, which is the proper big O classification? I'm pretty sure it isn't that one. Oh, nice. Okay, cool. And then do we have another question? Oh, here we go. How would we reduce O 2 times log? 2 times. Wait. You get rid of the constant, so it'd be log. Like that? Yeah. Oh my god, I might actually just... Hire me already. Constants quiz. Consider the following functions. So... I think they're just the same, aren't they? So they're both ON. Nice. Ignoring big O theory, which function realistically will take longer to execute? I mean, this has got one more step in it, I guess. So the total, yeah. So technically, I think double sum. Okay, here we go. O of 1 means that no matter the size of the input, there is no growth in the runtime of the algorithm. This is also referred to as a constant time algorithm. In Python, a dictionary offers the ability to look items up by key, which is an operation that is independent of the size of the dictionary. Okay. Dictionary lookups are of 1, which is one of the reasons dictionaries and dictionary equivalents in other languages are used all over the place. So we need to be able to search our locked-in user base more quickly. Our users are complaining that the search bar is painfully slow. You'll notice that if you run the code in its current state, it will take a very long time. The find last name function takes names dictionary, a dictionary of first name, last name string. If first name is a key in the dictionary, find last name returns the associated last name. Okay. The key is not found, it returns none. Okay. So we should be able to do, here we go with my Python skills. So if if it has first name, then I guess I'll return, I'll just return this. Else. How you doing else in Python? Return, and is it literally just none? Okay, I think that's right. I'm assuming that's because the key doesn't exist. How do you... I need my my Python cheat sheet. Hang on. Oh, Python cheat sheet. So dictionaries. So I need to check the existence of a key. Wait, that is right, isn't it? Yeah. But you can do this in. I wonder if that's like the better way of doing it actually. What is it? In it'll be first name in names.keys. Right. Oh. See if that works. Okay, there we go. Cool. Yeah, that was more of a lack of Python knowledge than an inability to code. Although I'll be honest with you, it's getting close. O-log n algorithms are only slightly slower than O1, but much faster than ON. They do grow according to the input size, but only according to the log of the input. This is where I start to struggle because I'm not really a math person, so like logarithms and stuff like that. Like I sort of get what they are, but they do. I just can't help but being confused, even though they're not that confusing. ON, so a second, yeah. Okay. Binary search, here we go. Okay, let's give this a try. So set low equal to 0. And then high to, I think you do, is it len? Like that. And then array -1. Nope, I don't need semicolons. And then you have to do a while loop. All right, okay. While low is less than or equal to high. Set the median, the position of the middle element, to low plus high. Is that meant to just be is this like a specific thing? //2? Or is that meant to just be /2? I feel like it's meant to be. Well, let's just go with it. We'll go with median low and it /2, or is //2 like its own thing? I don't really know. It's the problem not knowing Python. Okay, it's just giving me zip files or something. Okay. let's just try it like this first, and then we'll see. So, if oh, I need that. Array median is equal to target. Else, oh no, it's like L if, is it? List array median. Oh no, I just need to set median. Plus equals work, plus equals 1. Else median minus equals 1. Return false. Okay. So is that actually a thing? Okay, I think that is right. And then I spelt something wrong somewhere. There we go. Okay, it's missing something here. Anything about it? You start off with low at 0 and then high at length. So I need to change them, but I don't actually know what to change them to, and it doesn't say what to change them to. Try to think about this logically. So if this is less than the target, then I think we would want to set high to that, wouldn't we? Is that right? Something like that. High is median, maybe. But then, oh yeah, I completely misread it. What an idiot! No wonder that I. Right, okay. Yeah, it says. I'm just reading these bits that are like highlighted, so I'm like, I'm not following along properly. Set low to median plus 1. There we go. Okay, so low is equal to median plus 1. That's why I was getting it wrong. Otherwise, set high to median minus 1. See, that makes sense. That makes sense. That's why I was going to write that, like the a bit below it. But then I was like, well, why am I changing median? Because median's like set here, so there's no point. But Yeah, that makes more sense, right? So median plus 1, median, there we go. Okay, oh, there we go. I think that was it. 240 XP. So, yeah. But the thing is, I've done that before. I don't think I've really written it out that much. So, yeah, that's good. I mean, this makes sense to me, so that's good. Good start. All right. In locked in, we process tons of usernames. They are often structured as lists of lists. For example, a separate list of users for each influencer's followers. Complete the count names function. It should iterate over all the names in the nested list of lists and count all the instances of target name, then return the count. It should be O of n on the total number of names, but OMN if you consider m to be the number of lists. Okay. Let me just put count as 0, and then for is it lists? List of lists. Oh no, that's yeah, lists. Nope, not that. Okay. I wanted to go to the next parameter, but no, that's fine. Lists, and then do for again. Name. Actually, that's probably good in list. And then I guess if name is equal to target name, count 1. Do I return some? Oh, yeah, I return count probably. Okay. All right. So what's the time complexity? It should be ON on the total number of names, but OMN if you consider M. Yeah, that's good. All done. I think I'm on a new chapter now. Cool. Difficulty 6. Bloody hell. Yeah. Sorting algorithms. Almost every action you take in a web app relies on sorted data. Just looking up a user's profile in a database likely relies on a sorted index, which we'll talk about in another course. Fortunately, I wonder if they're going to do a course on creating a database. That'd be cool. I was reading through a book, but the book wasn't very good, so I couldn't really finish my database. But anyway, also I didn't know what I was doing. I was reading this book and it was talking about like B+ trees and sort of it started implementing them, but I didn't know what was going on, so that's why I stopped reading it. But at some point I do want to get back into like I think it'd be cool. There's like all these projects I have that I think would be cool. An operating system, a database. There was another one. Oh yeah, programming language, and I wanted to create a voxel engine, game engine. So I thought that'd be pretty cool. But maybe that'd be something to do on stream. Maybe. Be a lot of fun. So, fortunately, most programming languages provide their own standard sorting implementation. In Python, for example, we can use the sorted function. So we need to sort influencers by vanity. Complete the vanity and vanity sort functions. The vanity function accepts an instance of an influencer and returns their vanity score. The vanity score should be the number of links in their bio multiplied by 5, plus their number of selfies. Links in bio are weighted more heavily. But maybe I should just do this first and then read the next part, because it's going to get a bit mental. So vanity first. So number of selfies, number of bios in links. So okay. If I do vanity, I call it score actually. Score equals 0. And then influencer. I've actually never used like classes and stuff in Python. I assume it's just influencer dot and then it'd be the number of links in their bio. So num bio links multiplied by 5. Yeah. Oh wait a minute. Do score is equal to that. And then plus their number of selfies. Okay, score the influencer plus equals, not just equals. Influencer dot num selfies. Okay, so that's the first one done. Return score. Cool. The vanity sort function should return a list of influencers ordered by their vanity from least to greatest. You can pass a function as a named parameter called key. To sorted to control. Oh, do I need to add wait. Oh, okay, I see. You can pass a function as a named parameter called key. Okay, I see what that means. The sorted to control the metric the sorting algorithm will use for comparisons. Right. Okay, this is coming down to my complete lack of knowledge when it comes to Python. So sorted, and then it says I can pass in as a named parameter. So does that mean I can do like key vanity? And then influences. Is that right? I don't know if that's right, but we'll go with it. We'll give this a try. Invalid syntax. Yeah, I thought that might be the case. Let me have a look at this. Got to get the cheat sheet out again because I don't know what's going on. Here we go. So I can pass in. Oh, okay. I see. First of all, I think I need to pass this in first, maybe. And then it's equals like this, I think. Try that. 3 failed. Good. I didn't return. There we go. All right. And I'm guessing the next lesson is implemented sorted ourselves. Oh, bubble sort. Okay. Where if the standard sorted function exists, why should we learn to write a sorting algorithm? That's always the argument, and it's, to be honest with you, it's kind of the one I had for a while. I mean, it's good to know how things work, but that is kind of my argument. Was like, well, we're never going to implement it, but I don't know, it's a bit of a dumb argument, really. But we choose to write sorting algorithm from scratch, not because it is easy, but because it is hard. All right. In all seriousness, in this chapter, we'll be building. All I can think when I see this guy is Black Ops Zombies on the 5 map. Anyway, it's good to understand how they work under the hood, which is true. It's great algorithmic thinking practice, and it's fun, at least for me. I think it is fun. It's just really difficult. Like, I'd love to be able to do these things really easily. Like, I'd love to just kind of, you know, I'd love to like be able to write a B tree or whatever and do all the stuff and be like, yeah, this is cool, and create a database from it or whatever. Yeah, it's just quite difficult. But yeah, this is the whole reason why I'm doing this. Bubble sort is a very basic sorting algorithm named for the way elements bubble up to the top of the list. Cool. Okay, I'm gonna need to get my headset again and listen to this video.
Bubble sort is the sorting algorithm that everyone learns, but no one actually uses in the real world because it's so slow. We learn it because it's easy to understand, and once we appreciate how slow it is, the other sorting algorithms are just that much more impressive. It all starts with an unsorted list of numbers. Then we loop from left to right and compare each pair of neighboring numbers. If the number on the right is smaller than the number on the left, we just swap them. Otherwise, we just leave them be. When we get to the end, we just go back to the start and do it again. We repeat this process over and over and over until we go all the way from left to right without making any swaps. Here's what it looks like on a larger data set.
I like the music. Cool. Actually, no. Bubble sort. I mean, it's one of the few that I've actually like done. I sort of know how it works, but bubble sort is repeatedly. That was a good reading there. Bubble sort repeatedly steps through slice and compares adjacent elements, swapping them if they are out of order. It continues to loop over the slice until the whole list is completely sorted. Here's the pseudocode. Set swapping to true. The end to the length of the input list. While swapping is true, set swapping to false. Oh, okay, I see, yeah. And then we'll set it to true at some point else. Or I from the second element end. Oh, I see. Swap the I minus 1 element and the ith element, set swapping true. Decrement end by 1. Whew. Going to be a tricky one. Although it is meant to be the easiest one, but yeah, I assume I just need to do bubble sort. Like I don't need to do something specific. Okay, so set swapping to true. So swapping true. Oh yeah, it's capital T in Python, isn't it? And then end is the length of the input list. So len nums. And then we'll do while swapping. And we'll set swapping to false. Oh no, a bit one more, yeah. Whilst I is less than end. Is it less than or equal to, or is it just? We'll go with that, and then we'll see what happens, and then I plus plus. I don't. Do we need these? I don't think we do in Python. Oh. Go with that. So if the I minus 1 element, so we'll do nums 1 greater nums I. Okay, then we have to swap it, which is going to be that is right, isn't it? We do a temporary one, I think. I'm just trying to think which one needs the temporary value. Is it nums? Let's do I minus 1, minus 1, minus 1, and then we'll do nums minus 1 equal to nums I, and then we can do nums I equal to 10. Something like that. And then swapping through. All right, something like that maybe. Yeah, let me just check what a for loop looks like. Oh, yeah, okay. Hang on a minute. I remember this with Python. There was something that I think you have to do something like this. So for it not possible to just do a for loop with that? How do you do it in Python then? I guess, okay, I guess you can just do this. So we'll do I, num, and then, what is it? So in nums, I guess. So we've got the index, so maybe that's fine. God. There was a thing I saw literally just a second ago. Oh yeah, here we go. I think I have to do this. Enumerate. Oh, come on. Oh no. Oh god, yeah, it's a true. Honestly, most of this has just been like Python. Okay, I've definitely done something wrong here. Oh, I need to make it so that it goes from the second element up to end, but I don't really know how to do that in Python. Oh god, honestly. Maybe I can just use range. That maybe. It's a bit annoying that the thing that's slowing me down is the language rather than my inability to comprehend what's going on. Okay, let's have a look at the range function. So range 5. So we can start it from. Yeah, I think we can just do this. So we do I, and then we do range. Range from 1 to end. There we go. Like that. Okay, see, that worked. Except one failed. How did they all succeed and then one failed? 1, 2, Okay. They're all passing except this one here. So 9, 8. So it seems to fail on the 8 for some reason. I don't know, it feels like it works, but it's not working. Do I have to do end -1? No, I mean that just fails everything. Hmm. Yeah, I'm not too sure what I've done wrong here. Like I've written it the same way that this has been written, haven't I? Or do I always have to do? Oh, I might have oh, I think I might have put the end in the wrong place. Yeah. Okay, so it's outside of the loop. Oh yeah, there we go. Okay, what a dumb mistake. So it worked on the other ones, but it didn't work on. I guess. Yeah, I think this just had something that just wasn't on all of these other ones. I guess. Yeah, I put end in the wrong. I put the decrement in because I read it as like the decrement end by 1 should be part of this loop. I read it wrong. That's all good. At least it works. Thankfully. So, implementation reference. Oh yeah, and I did pretty much that, which is good. So, how the algorithm will perform based on the input data is instead of how much data there is. In the case of bubble sort and many other algorithms, the best and worst case scenarios can actually change the time complexity. Best case, if the data is pre-sorted, bubble sort becomes really fast. Worst case, if the data is in reverse order, bubble sort becomes really slow. Yes. All right. So merge sort is a recursive sorting algorithm, and it's quite a bit faster than bubble sort. A divide and conquer algorithm divide the large problem into smaller problems and recursively solve the smaller problems. Combine the results of the smaller problems to solve the large problem. All right. In merge sort, we divide the array into 2 equal halves, recursively sort the 2 halves, merge the 2 halves from form a sorted array. Another video. Let me just get my headphone.
First, let me explain the pros and cons of merge sort, and then we'll break down the algorithm step by step. Merge sort is much more efficient than bubble sort, which if you're here slogging through an algorithms course, you probably already know a little bit about. In big O terms, merge sort is order n log n, which makes it a lot faster than bubble sort's shameful order n squared. Now, order n log n is about as good as we can do when it comes to sorting unsorted lists. But there are a lot of things that affect performance on a smaller scale that are worth thinking about. For example, merge sort's space complexity is less than ideal. It requires copies of the original list to work with, which means it's going to take up more memory than an algorithm that can sort the list in place. It's also slower than some other algorithms like insertion sort when it comes to sorting smaller lists. And that's because of the memory allocation, the copying, and even the overhead of the recursive function calls. All those things have a constant toll on the performance of the algorithm. So they don't really affect the big O, which is order n log n, but they do affect the performance in practice. And that effect is disproportionately bad on smaller lists. Okay, so how does merge sort work? Well, first we start with an unsorted list of numbers. We split the list into 2 parts, and we keep doing that recursively until each list has at most 1 item. Next, we start merging each of those lists back together. The process is actually pretty simple. We take two small lists, iterate over each item in both lists at the same time from left to right, and we just compare them, moving the smaller of the two into a newly sorted list. By the time we've moved all the way back up the tree, we'll have a fully sorted single list. It's a recursive divide and conquer algorithm. It uses a pair of recursive calls at each level to split the list into parts, all the way down until we have a single element in each list. Then it merges them all back up the call stack again by looking at each element in both of the lists one at a time. It's an n log n algorithm because it needs to be called recursively log n times. And at each level in the recursive call, all items in the list are compared.
All right. Well, it sounds mental, but I guess there's a reason why it's like the second one you learn, so maybe it's not that crazy. But yeah, the algorithm consists of two separate functions, merge sort and merge. Merge sort divides the input array into two halves, calls itself on each half, and then merges the two sorted halves back together in order. Oh, God, I'm going to be honest with you. I've just been to the gym recently, like a couple of hours ago, and I am exhausted. So I'm struggling to read this, to be honest. I mean, I struggle to read at the best of times. The merge function merges two already sorted lists back into a single sorted list. At the lowest level of recursion, the two sorted lists will each only have one element. Those single element lists will be merged into a sorted list of length 2, and we can build from there. In other words, all the real sorting happens in the merge function. The length of A is less than 2. It's already sorted, so return it. Oh, okay, yeah. Got one in it. Split the input array into two halves down the middle. I'll merge sort twice on each half. Return the result of calling merge. Sorted left, sorted right. On the results, merge sort calls. Oh my god. I'm going to try and get this done. I'm going to be honest with you, I'm losing the ability to focus at the moment. Okay, so if the length of A is less than 2, it's already sorted, so return it. So if length nums, this is merge, yeah, okay, this is merge sort, okay. Then nums, oh, no, I didn't do the less than 2. So split the input array into 2 halves down the middle. Okay. I think that's right. And then something like that. And then, well, we probably want to do is it +1 on here? Maybe. We'll see. And then call merge sort twice, once on each half. Return the result in call of merge. Oh, okay, I see. So first half sorted is equal to merge sort half. And then second half sorted equal to merge sort second. And then return the result of calling merge first half sorted. And okay, I think that's merge sort done. And then merge is inputs A and B to sort of create a new final list of integers. Final. Set I and j equal to 0. I equals 0. J equals 0. Use a loop to compare current elements of A and B. An element in A is less than or equal to its respective element in B. Increment. Otherwise, I don't know if this is the right way of doing this, but we'll go with it. So if first less than or equal to God, that was awful spelling. And then J. I'm not too sure what to do for this last bit. After comparing all the items, I think that will do. There may be some items left over in either A or B. Add those extra items to the list. So, does it just mean loop through the rest of them? I have an idea of how that would work, but I just feel like it's going to get messy. But let's just try this. So if first, oh, no, actually, I need to do range. So range will be from I to -1. Oh no, that because it goes up to it, but then doesn't include it. So I think that's all right. Final dot. First I. Okay. Does this have to use J? Oh, I also messed up here, didn't I? Right. Is that right? I have to use J, I think. Okay, now. Um, Oh, okay. I was finding the middle point wrong, but everything else was fine. Okay, cool. All right. I think I'm going to end it there because my brain is failing me at the moment. But I've gone for an hour and 20 minutes. That's pretty good, and I've almost done that. I'll probably get that done. Maybe stream a bit later when I feel a bit more ready to go. But yeah, thanks for watching. Hopefully that was somewhat enjoyable. Maybe you can learn something from it. But yeah, thanks for watching.